Hi, Professor Cronin. Thank you very much for your time. And we are happy to have you in MetaStructure program.
It's good to be here.
Thank you very much. This program, as I already told you, is about MetaStructure, and we think different. And as you already, some months ago, I shared a post about your innovative way of chemical synthesis called Chemputer. And I received a lot of impressions. And after that, I read a lot of your tweets, your thinking about the problems. And we are happy to have you here in MetaStructure program. First of all, I would like to ask you about this Chemputer. If you elaborate what is Chemputer and what its concept and how you get interested in that way, and what are the potential applications of this innovative way?
Yeah, so the Chemputer is a programmable chemistry system that has reached universality in chemistry. The interesting about that is, for universality, we need to basically have a set of rules where we can basically encompass all chemistry as new chemistry rules. So it's a bit like, understanding mathematics. Your rules need to cope with new numbers, right? And so the Chemputer is kind of a minimal chemistry kit that can be programmed to do all of chemistry that humans can do, and possibly it can do chemistry humans can't do, but that remains to be seen. So the applications are for research and development, to invent new molecules faster, to do it safely. There are applications potentially for remote manufacturing. There's also a possibility of having, rapid development cycles between industry and academia. And so it also allows the chemists to go a lot faster than manually by doing chemistry by hand, and to go deeper into chemical space. And it's a bit like this. If you imagine thousands of years ago, when people used to travel by walking on their feet, you could only either travel from place to place where you knew there was food or water, or eventually you'd have to go back and get more water and more food. This is exactly what synthetic chemistry is like today. So when you start to do chemistry, you have a starting material, and you do the first reaction, and you'll have less material, and then the second reaction, and then less material, and you go on until when you want to go to make more material, you have to go all the way back to the beginning and start it again, step by step by step. If you could do this in parallel or without human intervention, then you can go a lot deeper, and so you can make more complex molecules more quickly. So the Chemputer is like an add-on for the chemist to search chemical space much more quickly.
And what are the applications in the field of chemistry?
As I described, for research and development, making new drugs, making new pesticides, inventing new materials, new formulations, anything that needs chemistry, the Chemputer can, in principle, help give access to, particularly on the discovery and the optimization side.
So it also has ability to design a pathway to a special molecule and develop a new molecule. Am I right?
Yeah, so because the system understands what reactions it's done before, and it has an inbuilt kind of, database, and it understands what movements it can make, if you like, it gets more and more blueprints. It's a bit like teaching a baby to speak a language. It will start by learning certain words, concepts, nouns, and it'll be able to string together new sentences. The Chemputer is not quite a baby, but what it is a system that is able to learn the rules of chemistry, given a certain subset of rules. And these rules aren't magical, they are anchored, they are rooted in the laws of physics. And hence having a precise system that's universal, like a Turing machine for a computer, allows the computer to become better at known chemistry. And in the end, the computer will be able to do all the chemistry that's known by the human race, and then go one step deeper. And so this is really exciting.
So interesting. In this way, you have went so far and deep, and many advancement made by your group about computers. And what were the main challenges you faced during this development and advancement?
Wow, lots of. I mean, at the beginning, because when you're running a research team, you have PhD students who are spending time to get their doctorate, and postdocs who are spending some time to kind of get some experience before maybe they'll go into industry or teaching or more academic side, or maybe a startup or something. So you have people that are obviously wanting to build things, and so what the challenge is to make sure the projects can sit together. I think, like, when I do research, it's like a relay race where you have a baton. The baton is the thing you're doing, and the runners are the operatives and the researchers and so on. And so the main challenge is to keep that research going, but a deeper challenge is to make sure you can bring together the disciplines required. So in this case, to build the computer, you needed to bring together computer science, electrical engineering, mechanical engineering, chemical engineering, chemistry, synthesis planning, reactivity, and analytics, at least. And this is just, this is 9, right? I wasn't even trying to get, and maybe the 10th one would be materials concerns. And so you've got 10 fields you have to bring together in one field. That's really scary if you're basically trying to get some students and postdocs in a team to build it and to do it quickly. And so what I try to do is, do it step by step and use the hardware that was already available. So really, I guess the main challenges are multidisciplinarity, building a team, reassuring the team and getting funding for the team to make this leap into the unknown. And also the other challenge is the discipline itself is quite resistant to change. At the beginning, everyone was like, why are you doing this? This is nonsensical. And indeed, today, some people are saying it's nonsensical. And so what I try to do is to point out the benefits for them: safety, reliability, the ability to share code, ability to train students beyond just chemistry and other disciplines, and data science as well. So I try to, receive the criticism with openness, and then try to convert that criticism to action to make the criticizers happy.
Yeah, it sounds very interesting that these too many different experts from different fields come together, and it should be very difficult to find a common language between them. Yeah. And,
well, I was going to say, I think the vision, once everyone saw the vision, then I think it really acted as a great motivator to say, yeah, we want to build this thing. So I think one of my job was not just to get the money and do the initial design with the team, but it was really to reassure them about the vision and that I would be behind them. But sorry, I interrupted you.
And what, from your point of view, what will be the impact of these computers in and pharmaceutical industry and pharmaceutical development?
It's too early to say what the immediate impact will be, but I'm pretty sure that the computer will change chemistry the way the computer changed mathematics. And that's one very, very large claim that maybe one should take with extreme humility. But why would I say that? Well, chemistry has been manual for a long time. There's a lot of chemistry to be done, and drug discovery isn't getting any easier. And we want to do things more cleanly. And so I think that there will be a massive change over the next 50 years. Chemistry hasn't changed that much digitally, and now things are beginning to shift. And the thing that I had to do first, which was really quite hard for people, was make the programming language for the computer. A lot of people thought I was just making it up or just making it more complicated. But the requirement to make a universal chemical system required a language that was universal. And so I think the impact will be very large, but what time scale? 1 year, 5 years, 10 years, 50 years? I think 5 years you'll see a major impact. I'm trying my best right now to make a major impact.
And are other also groups from other universities working on that way?
Yeah, I think there's a large number of people working in a similar way right now. Some people have slightly different ideas. Other people are kind of building on our ideas. There are people kind of collaborating with us, trying to do things. So I think it's really exciting. And part of my job is actually to kind of encourage people to work with us. One of the problems you have in science is that there are some people in science where it's very competitive and they don't want to necessarily follow what other people have done. They want to do new things, which is fine. But I think at some point it would be great for everyone to kind of get behind a particular approach or standard or technique.
And in your view, what are the most exciting advancements in the field of chemistry and chemical synthesis, recent advancements, I mean?
There's too many. I mean, there's so many interesting things going on in organic synthesis and metathesis and kind of almost like transmutation of elements, like changing carbon for nitrogen, for instance. There are people using photochemistry, electrochemistry approaches. There are big data approaches to controlling reaction mechanism. So there's quite a lot of interesting things going on. I think the increase in our computational capability has not yet been matched by our increase in our synthetic capability, and I'm hoping that is just about to come, but we'll see.
Also, as I read in your webpage, your group consists of 4 subgroups, and in one of those subgroups, your team are working on researching on origin of life and how your research can influence our understanding of the fundamental origin of life on Earth.
Yeah, I mean, the reason I built the computer was to make a search engine to understand the origin of life. But not the origin, as I say. It's really like, what are the chemical principles operating today where we can go from, nothing to something, right? And it's such a hard problem. But I'm hoping that the computer will allow us to do long-term chemical reactions, to look at reactivity, to understand the constraints of the program, the constraints from the engineering conditions that allow us to control the chemistry to do interesting things. And I think that is something that chemistry isn't really aware of. We pass knowledge from chemist to chemist through the textbooks and teachers and academics and so on, but that knowledge is not really given a very strong place encoded. And it's kind of interesting to watch how the reactions without that knowledge wouldn't work, but it's not written down very well. It's tacit knowledge. And I think that the problem with the way that we are approaching origin of life research in chemistry is we don't capture that tacit knowledge. And I want to understand, how did inorganic chemistry turn into biology through the medium of organic, bioorganic, and bioinorganic chemistry?
And it was your second goal, or because I read in your webpage that first you were a child, you were interested in making connection between computer science and chemistry, and after that you went in that way. And was that also your questions where you were a young scientist? Where is the origin of life, and where that change and how that change happens from inorganic chemistry to biology?
Yeah, I mean, I always saw, I mean, I don't know, right? Memories get replayed, but I remember being fascinated with computers and chemistry, and also biology, and understanding how can I make the connection between chemistry, computing, and biology, right? All around me, I was growing vegetables and looking at the insects and marveling at how these things were growing autonomously, and then looking at computers and how we run programs and chemistry. And I guess it was my and when I was a kid, I was interested in everything. I was taking everything apart all the time. And so I like to want to understand things. So I try to build a kind of new kind of understanding. So I wanted to understand the world of the computer and the insect and the chemistry at the same time. So it seemed natural to kind of say, well, if biology is just chemistry, and chemistry is programmed by biology using genetic code, where did the first programmer come from? How did that happen?
It's a very nice question. And also these days, after ChatGPT, everybody is asking about artificial intelligence and machine learning, how these AI and machine learning can help to development of chemistry and also in your field and also for your computer. Is it useful in that way right now or not?
No, I mean, look, the tools are useful, but not as useful as people think, right? There's not this paradigm shift. I think that ChatGPT might allow us to focus in on some chemical tacit knowledge that's not encoded explicitly, but indirectly. So that's kind of interesting. Also, these AIs are very good at natural language processing. So we can say, take this text, tell me where the solvents are, tell me the amounts and all these things. So reading text has become miles easier. However, you have to pay attention because there are errors, hallucinations. The NLP can't be bothered, it would seem, just says, it's this, because maybe there's some distortion. But like anything, AI is a tool. And for me, and rigorously, AI is not AI. It's not artificial intelligence. It's autonomous informatics. So what that means is that the intelligence that we ascribe to problem solving and creativity is not quite what we get. But it doesn't actually matter for chemistry. Like for chemistry, it's like, can we use these tools to mine the literature, suggest new ideas from tacit knowledge that we hadn't taken as first order readouts, and perhaps maybe allow it to do some shortcuts, co-piloting, exploring the chemical literature. It's all good like that. But like with everything, it's vital indeed to make sure that we just check critically what is going on.
And also, it was some days ago on Twitter, I saw a tweet from you that you told people should not be worried about AI so much, and there are some other things that they should worry about. I would like to ask you what you mean, for what they should worry and should not worry.
So my opinion about AI, but I think there's more in reference to AGI, artificial general intelligence, and AI, is that lots of people are worrying about this. And the fact is, they're worrying about something that does not exist. That is not a thing called an artificial general intelligence. There is not even an artificial intelligence. The only intelligent machines that we know are human beings who have Turing complete brains. We don't even know to the extent that animals can do things that are Turing complete and therefore universal mathematics. That's the first thing to say. That's a fact, right? If anyone says anything different, they're just wrong, right? That doesn't mean it's not possible. It will be. But what AI is very good at is generating lots of data or pseudo data, building on things, allowing us to then kind of suggest new things. So AI, the things I'm important about is authenticated data and authenticated users, because I think in our social media, we don't want fake news, and we don't want people to be stealing data. Now, of course, there's this argument that AI should be allowed to steal your IP because, that's how humans work. And that's not really my decision. That's really society's decision. Is it ethical to copy, I don't know, some music, say the Beatles, right? And just copy the Beatles music and just sell it to people and say, no, it's mine now? Or is it ethical to basically generate new music from the corpus of all music, including the Beatles and everybody else, and just say, no, this is mine? And so what you're doing is you're taking copyrighted material and then generating something new. Now, because AI doesn't generate anything truly new, it only uses the data it has and interpolates and extrapolates. It's not novel in the way that we human beings create novelty. And many people watching this, listening to this, will argue with this, but again, they're just mathematically wrong, is really interesting. And so we need to educate people about what AI currently is, right? Get people used to how much do they want free stuff versus they want to basically reward people, creators, because if we and so there's all these interesting things going on. So I think AGI is not going to happen anytime soon. That doesn't mean we shouldn't worry about it, but we can worry about many other things, like asteroids have hit the planet before, so maybe we should worry about that. AGI has never happened on the planet before and is without precedent, and therefore it's very hard to put a probability on it. And there are lots of people in the AI religion saying the probability of AI becoming generally intelligent is X, and that's nonsensical. It's impossible to put a probability on something that has never happened before. It's just bad science. So we have three things happening. We have the AI doomers and the AI optimists, and then the AI pragmatists. And I'm a pragmatist, and I want to use it responsibly, and I think it's a great tool for helping do stuff. But really, we should look at the real consequences on our society in developing industries, if that makes sense. And then, and I think, look, we shouldn't let the tech bros randomly make stuff up, because they didn't really do the best job with social media and Facebook and so on.
And so you think at least in near future, these so-called AIs are not able to discover something or make some invention?
So let's be clear. They are able to come up with new compositions, right? But those compositions, if you looked at their algorithms, you should be able to take the training set they've got, which is a fixed training set. You should be able to then look at the neural network, the deep neural network, how that's been trained with that training set. And then you should be able to put a query in and turn the cog and get out the answer, right? Now, if you do it at different times, you will get out different answers because there'll be different states in the system. But ostensibly, nothing magical has happened. It's mathematics. And so do you call that creative? Do you call that new? Sure, if I add two numbers together, then I will get a new number. And if maybe I've never said that number before, that's a new number to me. But does that mean that's a new number that's never been said before by another human being? It depends how large it is. And even then, does that mean it's interesting? I think that AI only tells us about the past, the training in the past. My biggest fear with AI is it's going to make the human race dumb, lazy, and uncritical. Dumb because we'll just not create any more content that's generally novel. We'll just keep generating content that is obvious from the corpus of content we have already. And people might argue that's the only content there is to generate. But I think it's easy, again, mathematically, to demonstrate that's false. So I don't know. I mean, as you can gather, I have strong feelings. I'm no, well, I suppose I am expert in that I do write AI models and I do train AI models and I do play with them. Okay, they're not that good, and I'm sure OpenAI and Anthropic and now Elon Musk's new company are going to do much better than me. But I know how to build them, and I know they're not magic. And I know, it's funny how people are worshipping silicon. It's the new god. And I think it all came from, actually, the reason for this is that Nick Bostrom wrote this book called Superintelligence. And this book kind of suggests that there is this thing called superintelligence without actually explaining what it was. And again, everyone went crazy and assumed naturally that AIs would be superintelligent without a definition. Sure, my computer can add up faster than me. Does that mean it's superintelligent? No, it means it can add up faster than me. So we need to start to have a sensible, critical conversation before we just jump to random conclusions.
Thank you very much for your views. I always was curious about asking this question because I followed your tweets. Always you were keep telling that this AI is not a real AI, and now I got an idea how it is, and also there is something else, as already you told. There are some bigger stuffs we should worry about, and climate change maybe is one of them that everybody in every place are worried about that and are talking about that. How your work can help to tackle with this climate crisis?
I mean, I don't think my work per se is going to do very much for the climate crisis. I guess computers could make things cleaner and cheaper. It would be nice if we did one fantasy I had is if I could make a new type of inorganic life form that could be better at fixing CO2, we could basically do some geoengineering. You know, the fantasy I have is if we could make a new type of material that could take sunlight, carbon dioxide, and then fix it into some form of carbon that could either be recycled and burnt, so we have a circular economy, faster than fossil fuels, because fossil fuels, that happens for fossil fuels, it just happens on a geological timescale, and that is not good for human race. Or we could find out with another way. But I think the issue that we have with climate change is we're just not being, again, we're not being sensible. Like the current climate doom is we're telling everyone, oh, it's all going to be terrible. No, actually, it's not. If the planet heats up, we'll actually have more greenery, we'll have more growth. Sure, there's going to be things going wrong, and sure, there's going to be all of this, that, and the other, and sure, there's going to be massive displacement of people, which is terrible, right? I'm not saying that that's a good thing. But what I'm saying, there are lots of people creating, again, the same AI doomers and the same green doomers are kind of not understanding. The human race is in a big race with itself, which is we need to create new knowledge and to create new technologies, and we need to create solutions to our problems faster than those problems get out of control. So I think that one of the things we might need to do is get to nuclear fusion so we can get enough energy to fix CO2 quicker. But again, it's way out of my pay grade and my ability to predict. I like to just, you know, everybody is being dramatic, right? It's kind of funny, but it's not funny, right? Sea levels will change, oceans will acidify, the ice caps will melt. There will be more wind. There's going to be a bigger engine. You know, there's more energy in the system, so there are more things going on. That's clear. But let's balance the two things: human progress, pulling people out of poverty, and people living longer and less infant death every year compared to deaths from climate change. Is human progress beating deaths from climate change by many orders of magnitude? Yes. So should we start to basically slow down progress because of climate change and just give up and not eat meat and not fly and not turn on any electricity, you know, have any kind of, you know, vast amounts of electricity being used? I mean, I think that's not for me to answer. That is society and our politicians. I think it's really interesting. I would like to do something to be helpful, but I want to do something that's going to be helpful genuinely on a long enough timescale. And I just don't know what that is. I did my PhD in the fixation of carbon dioxide, actually, or actually understanding how carbon dioxide is taken from the atmosphere and stored in mammalian systems, an enzyme called carbonic anhydrase. And it's pretty, back then when I was finishing my PhD, it was kind of pretty boring. No one was really talking about climate change, and now we are. So I want to make a difference, but I'm not sure if I am qualified to make a difference really in the global debate. I think that politicians actually can make much more difference than scientists by coming to some kind of global consensus on how we're going to burn fossil fuel and how we're going to get access to energy. The thing that I think we should do like now is make it humanity's goal to get to near to zero cost energy by 2050, not zero carbon. So we get to zero cost energy by 2050, then we should be able to remove all the CO2 from the atmosphere. Right now, we don't have enough energy to remove the CO2 from the atmosphere. That's scary. So we're now into geoengineering and all the other stuff. I would say burn more fossil fuel if it gets you to fusion, because you can then basically use standard processes to get all the carbon dioxide out of the atmosphere.
Right, and as you told, that's one of your main suggestions. I've already seen many times in your Twitter that you supported this nuclear fusion for tackling with this climate change. And yeah, that's there is a problem, as you know. Germany already turned off almost all of its nuclear power plants due to an nuclear crisis happened in Japan. And they say it's more costly when something like that happens, that the whole energy we receive from nuclear power plants.
But that's, yeah, I mean, I don't want to criticize Germany, because Germany are doing a great deal to kind of decarbonize. They're trying, right? But here's a couple of observations. The very green movement that is now giving us lots of existential doubt, right, which I can understand, was the same green movement 30 years ago that stopped our best chance of getting to nuclear fission quickly and more reliably. And that's really ironic, because one of the reasons why we're burning as much fossil fuel now is we don't have nuclear power stations. Now, if you look at France has got a lot of nuclear. The UK should both go nuclear. Germany should go nuclear. And the comparison between Germany and Japan is completely false, because there's no tectonic activity. And of course, and no one could have predicted about the Ukraine invasion by Russia. Germany didn't predict that. So, you know, it's kind of like I have sympathy. But I think now we should be able to design with modern methods nuclear fission reactors that are cheaper, that produce waste that's manageable and modular, and deploy them at scale. And we have a lot of nuclear power, a lot of nuclear fuel that we can give around. And I know if people are worried about terrorism, but if we can use this free energy to drop the poverty, to remove poverty all around the world, then there are going to be no terrorists wanting to make nuclear dirty bombs, right? Because we won't have that as a problem. But maybe that's me being too idealistic. But the thing that I am absolutely critical of is that people put a stop to nuclear power in the 70s and 80s, or even earlier, stop the generation of cheap energy. They argued it wasn't cheap. They argued with all this stuff, and maybe the technology there was some argument to be had. But would we rather subsidize nuclear power or fossil fuel? And I think, you know, because it's quite clear that there's some people in the world fortunate enough to not need fossil fuel. So they're all like thinking, oh, we're great, we don't need fossil fuel. But if you think about countries like China and India and Southeast Asia and Africa, they need fossil fuel. We cannot turn off fossil fuel like that. It's kind of insulting and humiliating. Well, not humiliating. It is inconsistent with our current moral and ethical values for the human race. But, you know, look, my Twitter is my personal Twitter. I get into trouble for my Twitter all the time. I like to basically kind of get people to think on Twitter, but hopefully they don't take it too seriously, because I'm very good at being wrong and being ill-informed and these things. I try to do good chemistry Twitter. I try to do good complexity Twitter. I try and do good computation Twitter and good AI Twitter. But other things, I'm just rubbish.
Thank you for this information. Yeah, that's the main thing that we were interested and fascinated to invite you to this meta structure, because you had different ideas from the mainstream of scientists. You had different views about the problems, and it's very interesting. And the other thing I would like to ask you about is the use of 3D printing in creation of complex molecules, and especially in pharmaceutical and also materials development. What it is exactly, and where we are, and what are the potential use of that and ethical views about that?
Well, the 3D printer actually is not really printing the molecule, right? Well, it is printing molecules, but it is not making the molecule via printing. What I've been doing is printing reactors that then people use to then do chemistry in those reactors to get new routes to chemistry and so on. And I think that's pretty interesting. It allows chemical engineers and synthetic chemists to think in a new way. And I think that's really important. If you're a synthetic chemist and you're doing reactions in your glassware, manual reactions, if you could 3D print your own custom reactionware, would that make your life easier? And that allowed us to design a whole range of new chemical robots, which were like the computer, but miniature versions. And also we use 3D printers to make kind of milli-fluidics and micro-fluidic systems. So they're quite interesting that way because it drops the cost. And yeah, it's just a really good tool to get people kind of, building new things and thinking slightly differently. So that's the main reason. And actually for me, the use of 3D printers and the 3D design tools to make new chemical reactors educated me in thinking about more engineering principles. And I think my colleagues in the chemical engineering find it quite funny because they're like, Lee doesn't know anything about chemical engineering and he's just discovered it through 3D printing. Oh gosh. And that's true to some degree, but the other degree is I was then able to bring chemical engineering principles into the chemistry laboratory and explore them. And so that was something I was super excited about. And it was an excuse to combine robotics, chemistry, and design all and a bit of electronics in the same place. And I think that's really important for our students and our researchers to make it more fun and more integrated.
Thank you very much. And is it, there is a problem that it is already some single-use reactors, chemical reactors made out of polymers, and the main problem with them is a lot of waste that they produce. Also, they are very reliable about cleaning stuff. Don't you think there will be also the same problem with using 3D printing for this designing these reactors?
For sure, but I mean, I'm not sure I'm advocating that they should be used for mass distribution. What we were using them as for a conceptual design tool to come up with new ways of doing the chemistry. But also, you could recycle the polymer and decontaminate it. It's not that tricky. And maybe the cartridges could be reused, right, after washing. And so, I think that we do produce a lot of plastic waste right now, and we've got to learn how to recycle that. So I think, if anything, if we understand how we're producing this waste and what the benefits are and the cost, and as long as we cost in the recycling and decontamination, then we can make a comparison. And I think this is, doing whole life cycle analysis is so tricky nowadays. I mean, how much energy does it require to produce glass blowing, and the reuse get out of glass versus plastic? Well, I think it's pretty clear. Glass is loads better than plastic. You can use it thousands of times, right? And the energy gone into it is just one-time thing. So it's kind of interesting. We have to think about that carefully. But really, I'm about doing new things to get to think in new ways. And in some area, they might allow us to go, do it differently. You can get glass printers now. And so one day I'd like to basically, when the technology's come on enough, is to do some glass printing. But I must say the glass blower that I work with at the University of Glasgow is amazing. There is no way you're going to replace this guy with a 3D printer. He is a genius. And also he's able to work with my team and create really interesting art. And so actually a lot of the 3D printing we've done in plastic, we take to the glass blower to show what we're training. He goes, oh yeah, right, I can do that. And so it's kind of funny that we go through all the kind of prototyping stages in plastic. So we then go to the glass blower to do it properly when we need to. And that was something I didn't expect. Because at the end of the day, I was like, we should use the 3D printed stuff. And I was like, actually, no, we should use glass. It's cleaner, it's better, it doesn't break. But the process of the 3D printing the reactionware allowed us to conceptualize in the design process how to build the best reactor for the process we wanted to do. And today that remains the case. It's awesome.
About your research, I would like to ask you what directions your upcoming research, what is the direction of your future research, in near future and middle future and long term also?
Just all the questions. Well, I want to explore the world of chemical computing to basically make sure it really is universal. And I would like to discover chemical reactions that couldn't be discovered by humans on their own. I want to be able to make a search engine to basically look at how selection and evolution starts before biology. We now have a theory that gives us a way of measuring it, right? Lots of people have been arguing about this assembly theory, but actually there is a fundamental new way of measuring it in the lab. It's experimentally measurable. So all the arguing they can do is just like, so they're kind of arguing like, oh, it's a bit like this, a bit like that. And I'm like, no, you can measure it. Yeah, I build it to be a measure. And so there's kind of, that's really funny. So we're going to use that. So we're building selection engines right now, and we're seeing if we can actually see how life can start to make those very first steps in the lab. The other thing is I want to make, and I've talked about AI, so an AGI, I want to see if I can make one, right? Having said AGI isn't possible yet, I'm interested in understanding what is it about the human brain. So you think about the human brain can be traced back 4.2 billion years to the last universal common ancestor, Luca. Luca was on planet Earth for, a few hundred, if not billion years, and then suddenly prokaryotes, archaea and all that turned into eukaryotes. Then a few more billion years went by, and then suddenly we had animals and plants and so on. And then we had, primates, and we had abstraction, okay, and the ability to kind of, build technology. So I'm really interested in, and then the human brain, something happened in the human brain that allowed the human brain to develop language. And we developed language, we developed consciousness. And consciousness at a high level, because I'm sure animals are conscious, cats are conscious, dogs are conscious, some animals all the way down to the ant, right? It's conscious, but not that much. But humans have a special type of consciousness that we don't understand the physics of. That doesn't mean there's anything magical going on that's quantum. I mean, we merely don't understand what it is about physical reality that allows human brains to create novelty. And the human brain is just a gel with some cells in it that are 4.2 billion years of evolution. So I'm figuring, what can I make a chemical brain? And that's one of the things I'm trying to do for fun, and see if I can program it. A kind of chem machina.
Very nice. And do you think also there is a potential for use of quantum computing in this field? Or you are thinking about that?
I mean, I don't know very much about quantum computing. I know a little bit about quantum theory. I am very interested to see if the various barriers for technical implementation of quantum computing are overcome. And, I was a little bit skeptical, but people are making progress. That's really interesting, because at some point soon, the error correction and the technology will progress, will lead us to see a fully blown quantum computer, or it for not to materialize because there's something wrong with quantum theory or something like that. I mean, quantum theory isn't quite right, or general relativity isn't quite right. One of them isn't quite right. So they're going to need some modifications anyway, but I'm just not qualified. What I would say, though, is I'm very interested in using maybe some quantum devices to help solve chemical problems, to make new materials and new molecules, whether that's in a quantum simulator or some kind of quantum computer or some other manifestation of ability to encode quantum states and look at their time evolution and use that readout, the time evolution, to help us design something new. That would be super cool. And so I'm just, I'm just watching this area very closely, but I'm not qualified, and I think it's kind of better for me to not have never say, quantum computers do not appear to be impossible, but we don't know what quantum theory does yet. So that's one question. And we don't know practically how easy error correction or how hard it's going to be. That's another question. And then once we get there, it's not clear how good or useful a quantum computer is going to be. But it's going to be amazing that people are trying, and there's a lot of investment, a lot of smart people who are going to do this. So I'm excited to watch them. If I can connect my computer to a quantum computer, I don't know what that would do. Probably some crazy stuff. And
also, I have another question before the last question. There are a large group of researchers that they focus on simulation in molecular scale and atomistic scale, and some people say, some of those researchers say one day these simulations will substitute the experiments, and some other people, they are critics of them and say they are exaggerating the possibility of doing that and doing everything with simulation. What's your point of view about these two groups of people? And
I think it's simple to demonstrate that simulations will never replace reality. Why? Because there's levels of abstraction, right, that we have. That now simulations are good at certain things, and they'll get better. But the overclaiming here is kind of funny, because you have computational irreducibility. There are some things that nature does that we can't seem to really evaluate very well computationally. And this is really interesting. It's a very important feature of mathematics, but more kind of mundane than that. Things emerge at higher levels, and unless you have some kind of framing for the emergence, it doesn't, because the simulation doesn't contain enough information. If you want the emergence to occur, your simulation has to be at least as large as the universe, right? In the worst case scenario. That's a really big computer. And that's the size of the universe yesterday, when the universe was smaller and there was less time. Now the universe has got bigger and there's more time. You're always building a bigger computer. So you never catch up. And so I think that it is kind of a category error to even compare them. Simulations are going to get better. Look, if you look at the weather predictions we've got right now, they're like amazing. If you look at how we do atomistic simulations, simulating things. But if you look at LK99, this so-called superconductor, the guys at NIST did a simulation and said, yeah, we can see the possibility of it being superconducting. And that was just like, no, it's not a superconductor. It's a salt. And that doesn't mean the guys at NIST were bad. They did really good calculations and they showed a really interesting phenomena. But it's at what level of emergence and abstraction? And so people that say that they can simulate everything basically that's code for saying, I'm God and I understand the entire universe. That's clearly not true. And therefore, same way that, many mathematicians have known this with incompleteness, that the pursuit of science is about the pursuit of knowledge. And because the pursuit of knowledge is never going to end, a simulation is never going to be able to simulate everything. It's just like a kind of, I don't even know why I would say that. It's so easy to refute.
And so you think simulation is somehow useful for optimization?
Very useful. Simulations are amazing. Simulations are so good at telling us lots of things. I don't understand why people need to say, you never need to do another experiment. Experimental theoretical simulations with boundary conditions from experiment are amazing. If you don't have the boundary conditions from experiment, you kind of you haven't got a ground truth. And that means you have to simulate the entire universe. And you can't do that. We have to take a shortcut. So if you can't simulate the entire universe, use an experiment as a starting point, do a simulation, check, update, do it. That is that simple. That's why simulation is beautiful for experiment. Experiment is beautiful for simulation, especially when you then can develop a predictive, explanatory, underlying theory. And it's, you know, it's like, it's kind of insane to suggest that one is better than the other. They are absolutely vital.
Yeah, thank you very much. And for the last question, if you have any advice for young researchers and scientists, and if anything you want to add to this interview, I would like to hear that.
That's a big question. It depends. I mean, I would say to younger people, obviously pursue what you find really curious. And I think it's super important that you, care about it. You have passion about it, that you're able to poke, and don't be afraid of, upsetting the current orthodoxy. I think that, a lot of people kind of tell me, oh, it's okay, you can do this because you're just rude and you're this. And I'm not rude. I'm not rude. I don't want to be rude. I just want to challenge people to think, learn something, because I inhabit a world. I'm so fortunate to inhabit a world with very, very smart people around me, much smarter than I am. And I want to, if I can get all these smart people to think and tell me what they think, I might get a little smarter, just a little bit. So people misunderstand my humility, trying to kind of get not ideas, but kind of feedback from smart people about what they think about the idea, trying this. And so I think that young people don't do that enough. They're too worried because, we're not allowed to be critical anymore, and being critical is like kind of hard. And I think that's complete nonsense. You have to be highly critical, but you can be critical without the idea. You don't have to be critical about the person. So I say to young people, be critical, be playful, don't worry when it's wrong, and try and have fun. And if you're having fun at the end of the day, then you're winning. Because at the end of the day, if science isn't fun, then why on earth are we doing it? And, other than generating knowledge and saving humanity from the heat death of the universe. But that's my last goal.
Thank you very much. And thank you for your time. And yeah.
Thank you.
And have a nice night.